So there needs to be a better way of implementing this cipher. And as is the case with many ciphers, what helps us to get back to our conversion table is a little bit of number theory. Number theory forms a very critical, necessary, first ingredient to a lot of crypto schemes. And number theory is basically the study of integers. And one major branch of number theory involves what's called modular arithmetic. And it's called that because you're doing arithmetic with remainders. And there's going to be something called a modulus, which is essentially a divisor. And as you're probably aware, if you were to divide a random set of numbers by, let's say, the number 7, a lot of those quotients would yield some remainders that are the same, across the different numbers that you're trying to divide by 7. In fact, any number that you try to divide by 7 is going to yield a remainder anywhere between 0 and 6. Okay, so with how many numbers we could possibly divide by 7, in terms of remainders, it's only fixed to those 7 digits, 0 through 6. And so a lot of remainders repeat when you use a divisor. And that's kind of, a key observation when it comes to modular arithmetic. In fact, we have this definition coming up where it says if m is a positive integer and a and b are any, that should say integers by the way, we say that the integer a is equivalent, also known as congruent, to b modulo m, which is written this way, a and then a 3-bar equal sign, that's a congruent symbol. We say a is congruent to b modulo m if a minus b is an integer multiple of m. In plain old English, what that means is a minus b is divisible by m. Another way of saying this is as follows. A and b have the same remainder, upon division by m. Let's say we look at the numbers 13. Let's say we have a equals 13 and b equals 20. And I'm going to stick with a divisor, which in this case will be a modulus of 7. I'd like to see what remainder we get when we divide both 13 and 20 by 7. All right, and I'm going to go old school with this. So I'm going to draw the division hut, and I'm going to put 13 in there and 7 out in front. And then we can do the same setup with b equals 20. All right, so let's try and divide 7 into 13. How many times would 7 go into 13 without going overboard? One time. Yep. Then we do 1 times 7 to get 7. And then don't we subtract? So we get 13 minus 7, which is 6. Now 6 is going to be our remainder. And the reason why it's a remainder is because 7 is too large to fit into it. And that's where I'm going to leave it. I'm not going to go any further to add the decimal point and so on and so forth. Let's try to divide 7 into 20. How many times can we fit 7 into 20 without going over? twice. Yep. So we put the 2 on top of the division hut, we multiply 2 and 7 to get 14, we subtract, and we get 6. So again, this is another scenario where 6 is going to be considered our remainder because 7 is too large to fit into it. So since the remainder in each case is 6, what it implies is that 13 is congruent to 20 mod 7. Okay, now that's using this version of the rewrite of the definition. Okay, A and B have the same remainder upon division by m. Let's look at A minus B and see if that's divisible by m. Okay, if we do A minus B, that's going to be 13 minus 20, which gives us negative 7. Is this number divisible by 7? So I'll pose a question, divisible by 7? Yep. So because A minus B is divisible by 7, this also implies that 13 is congruent to 20 mod 7. Okay. Now, because 13 is congruent to 20 mod 7, I'm going to say this. This also means that 6 is congruent to 20 mod 7. Think about it. If we were to divide 6 and 20 by 7, the remainder would be the same. The remainder would be 6. Okay? It's kind of a special case using the number 6 because if we go to set up the division hut with 7 on the outside and 6 on the inside, we couldn't fit any copies of 6 into, I'm sorry, we could fit no copies of 7 into 6, and so we'd be forced to put a 0 on the top, giving us a 0 underneath the 6, and when we subtract, we get our remainder of 6. So I'll give you a little tidbit about congruences. It's always possible to keep what's called reducing a number until it's smaller than the modulus. Because any number that's bigger than the modulus, we could always fit the modulus into and get a remainder. So as some additional examples, let's look at part A. It says here that 7 is congruent to 3 modulo 4. There's a couple ways of verifying that. I think the easiest way to verify that is to see if 7 minus 3 is divisible by 4. So if we do 7 minus 3, we get 4. And 4 is divisible by 4, isn't it? In fact, you can write this as 1 times 4. And to say that 7 minus 3 is divisible by 4 means that 7 minus 3 could be rewritten as a product where one of the factors is 4. And that's the case. For part B, negative 5 is congruent to 3 modulo 4. And to verify that, we could do negative 5 minus 3, which gives us negative 8. And you could rewrite negative 8 as negative 2 times 4. So the fact that A minus B can be rewritten as negative 2 times 4 means that 4 divides A minus B. So this is a true statement as well. For part C, if we did 30 minus 4, that gives us 26, which we could write as 1 times 26. And because we can write that subtraction as a product involving 26, 30 would be congruent to 4 modulo 26. So if this is all gelling with y'all, I'd like you guys to maybe offer me some potential answers to parts D, E, and F. So let's start with part D. Anybody want to throw out a number that they think is congruent to 26 modulo 26? Zero would work. Yeah, perfect. Yep. That's called the smallest positive residue, by the way. But to verify this, if you did 26 minus 0, you get 26, which is 1 times 26, which implies that A minus B is divisible by 26. Do you think this is the only answer to this problem, though? Could we have put instead the number 26? Yeah, we could use 26 instead, because 26 minus 26 is 0, which of course is divisible by 26. Anybody want to offer a possible solution to part E?
12.
Perfect, yep. 12 works. If you did 25 minus 12, you get 13, which is 1 times 13. Bingo, you got it. Nicely done. Anybody want to offer a solution to part F?
58.
58. Okay, so if we did negative 8 minus 58, that gives us negative 66.
Can we do negative 58?
Say it again.
Can we do negative 58?
Okay, let's try negative 58. Okay, if we do negative 8 minus negative 58, that's negative 8 plus 58, which gives us 50, and bingo, you got it. That works. Here's another potential answer. Could do 42. Could you see why 42 would also work? If we did negative 8 minus 42, that gives us negative 50, which is negative 1 times 50. So that works as well. So folks, there are many, many answers that we could provide for these congruence statements. In fact, a secret to generating more and more of those answers is to just continue adding the modulus to whatever answer we had put in originally. So for example, with negative 58, if I add 50 to it, that's equivalent to taking negative 58 and adding 0, because 50 is congruent to 0 mod 50. Now, in real life, negative 58 plus 50 gives us negative 8, which confirms that, negative 58 is one of our answers. But if you continue to add 50s, to each new number, you get more and more answers, and so there are infinitely many answers to something like a congruent statement. So I had mentioned the word residue, and there's a reason for it. The positive remainders, the smallest positive remainders, are called residues. So when we, when dividing by 7, the remainders are one of the following: 0, 1, 2, 3, 4, 5, and 6. We wouldn't include 7 because that would have the same remainder of 0. We wouldn't include 8 because that would have the same remainder as 1, and so on and so forth. So it turns out that when you select your modulus m, you can infer a set of remainders tied into it. In fact, the remainders would go 0 all the way through 1 less than your modulus. And if you look at our set of remainders for the number 7, we have 0, 1, 2, 3, 4, 5, 6, and obviously 6 is equal to 7 minus 1. And these are called residues. And there's a special notation that we assign to the set of residues. It's the symbol z for integers sub m. So that would represent the set of integers modulo m. In our particular situation, if we form these remainders as a set, this would be equal to z mod 7. Okay, because those are all the remainders that we can get when dividing by 7. So when it comes to Hill ciphers, we now have a way of handling entries of the ciphertext vectors that are larger than 26. Case in point, let me go back to that page. Actually, no, it's okay. We had 36 and 24. That was a ciphertext vector that we had issues with. We also had issues with the vector for our original letters R and O. It was 48 and 45. Then we had an issue with the CK part, 25 and 33. And then we had an issue with our very last vector, which had the entries 29 and 15. Now what I'm going to do is I'm going to do what's called reducing modulo 26. And you can probably guess as to why I'm using a modulus of 26, because that's how many letters we have in the alphabet, the English alphabet. And so I'm going to say that, in order to handle the 36, I'm going to say that this vector is congruent to a number in the first entry, which is 36 modulo 26, whatever that reduces to. And 24 is smaller than 26, so we don't need to do any reducing for that value. But let's think about it. If I had asked this question, 36 is congruent to blank mod 26, what would you put in for the blank? How about 10? What do you guys think about that? Is 36 congruent to 10 mod 26?
Yeah, I think.
Yeah, yep, you're right. Yeah, because if we did 36 minus 10, we get 26. So instead of using 36, we could reduce it modulo 26 and get 10. Which means that the letters that we encrypt the plaintext letters to would be, let's see, 10 corresponds to J, and 24 corresponds to X. let's reduce these two values modulo 26. And I'll show you how to do this using the calculator. Okay, so I'll do 48 with you on the calculator, and then I'll give you a shot with 45. And if you feel comfortable enough, I can give you a moment to work on 33 and 29. All right, so if you have your graphing calculators on you, let's go ahead and get those ready. This is a helpful skill, especially when the numbers that we're trying to reduce are very large, which is usually the case in cryptography. They use very, very large prime numbers as moduli. But anyway, let's press the math button. Okay, so let's press math. And then we're going to arrow over to the number column. And I'm going to shortcut going all the way down by pressing the up arrow key. And I'd like us to go to option 0, where it says remainder. Okay, anybody need me to repeat that? Okay, let's press enter. And we're going to put two numbers in the parentheses separated by a comma. The first number is the number that we're trying to reduce. And in our example, that number is 48. Right above the 7 key is a comma. Let's go ahead and press that. And in the second and final slot, we're going to type in our modulus, which is 26, and close off the parentheses. If you press enter, your calculator gives you 22. So what this means is that 48 is congruent to 22 modulo 26. And if you think about it, we could check it doing 48 minus 22, which gives us a number that's divisible by 26. So 22 is what we should use instead of 48. Okay, so instead of 48, we'll do 22. All right, can you guys go ahead and try reducing 45 modulo 26? And then you can report the answer in the chat. Yep, I agree, 19. So the ciphertext for the two letters that gave us that vector would be V and S. All right, so go ahead and reduce the next two vectors, modulo 26. After a minute or so, I'll check in with you to provide what I got, and we can clinch that example now that we have some number theory under our belt. Yep, I can do that. Okay, so you'll press math and go over to the number column, and we're going to go up to number 0. So far, so good. Okay, press enter. And for 33, if you want to do that, we'll type in 33, press comma, and then type in 26. And press enter, and we should get 7. Did that help out? No problem. So 25 can stay as is. 33 reduces to 7 modulo 26. So the two letters that we should get out of that are Y and G. 29 would be congruent to 3 modulo 26. 15 does not need any reducing. So this yields the two letters C and O. All right, so let me go back to our message here. It's OC sorry to keep going back and forth. OCJ, actually, you know what, let me write it here. OCJX, and then VS, then YG, and then CO. So this right here is the encrypted version, or in other words, ciphertext for Math Rocks with E. Okay, makes sense? All right. So where the modulus is 1?
Yes. The formula m minus 1 means it's 0.
Oh,
I'm a little confused about how you do the residue in that situation.
yeah, actually, okay. So if m is equal to 1, then the residues would be just 0. That would be the only remainder that you could get upon division by 1. So, for example, if we took 13 then one potential answer for 13 would be 0. And that's because 13 minus 0 is 13, which is 13 times 1.
If the number was 13.45, wouldn't there be a remainder then in that case?
Right, but let's look back at the definition of these residues. It says integers in the set. So when we're doing the modular arithmetic, we're assuming that a and b are both integers.
Okay.
So for something like 13.5 or 13.45, that's not an integer. So that wouldn't really conform to our set of residues unless you redefine what you're using when performing modular arithmetic. So if we allow, I'm sorry, go ahead.
No, I'm following you. I wasn't sure if you could use modular arithmetic on numbers that had decimals that weren't integers.
Oh, you absolutely can. Yeah.
Okay.
So if we allow the numbers on the closed interval or half open interval 0 to 1 as remainders, 13.45 would be congruent to 0.45 modulo 1. Yeah, so if we tweak what we're allowing as remainders, then yeah, we could do something with 13.45. With the way I have the residues set up, they're only allowed to be integers. So something like 0.45 wouldn't really belong in that set. But you're right. If you allow any number between 0 and 1, 0 inclusive as remainders, then we could definitely do something with 13.45. And what that would be congruent to is 0.45. And you could establish that fact by using our definition. If we did 13.45 minus 0.45, that gives us 13, which is a multiple of 1. So it checks out.
Right. Thank you for that clarification.
No problem. Okay, so one of the more difficult aspects of this all is when it comes to multiplication. We know with the set of real numbers, provided you're not the number 0, there's always going to be a multiplicative inverse or some sort of reciprocal for which we can multiply the two numbers together to get the number 1. Well, that's not always the case in modular arithmetic, and there's some results in number theory that allow us to establish when a number is going to have a multiplicative inverse and when it won't. And it all has to do with very basic mathematical ideas such as greatest common divisor and things like that. And then there's something called the Euler phi function, which gives us an idea of how many of those residues would have multiplicative inverses, should you divide by modulus m. In this definition, it says that if A is a number in the set of residues, then A inverse, which should come from that same set, is called a reciprocal or multiplicative inverse of A modulo m. If the following happens, we can multiply the two numbers and establish that the remainder is 1 upon division by m. So these are a little difficult to find when the modulus is big, but I'm keeping the modulus small in our upcoming examples. That way we can kind of figure these out in our heads. To find a multiplicative inverse, modulo m, it boils down to solving a congruence equation. You have to basically pick a number from the set of residues, multiply it to whatever you're trying to find the inverse of, and then check that the remainder would be 1 upon division by m. One of the results in number theory says that this congruence is only solvable if A and m have no common divisors other than 1. We say that they're relatively prime in that case. Now, in practice, in real life, this modulus m is typically a very large prime number because it satisfies two things at the same time. Number one, the numbers are crazily large. So, it's going to take a computer to try to even do anything with it. Number two, any number leading up to that prime modulus will only have a common divisor of 1 with the modulus. When we start using composite numbers like 26, there are some numbers smaller than 26 that are divisible by something other than 1. For example, 13 and 26. They're each divisible by 13, so that wouldn't really help us out in this case. So when you have large prime moduli, you're in business to start forming a good crypto scheme. Now, in this example, we want to find the multiplicative inverse of each number modulo 5. Now, let's keep in mind what modulo 5 looks like, the set of residues that is. That's going to consist of the remainder 0, 1, 2, 3, and 4. Now, every number in this set is relatively prime to 5 because the only divisor of any of these numbers with 5 is 1. So every single number in here should have a multiplicative inverse. Now, if we try to find the multiplicative inverse of 3, we'd have to solve the equation 3 times x is congruent to 1 modulo 5. So let's kind of guess and check here. Obviously, 0 is not going to work, right? Because 3 times 0 is 0. And if you do 0 minus 1, it's not divisible by 5. If we check, if we assume x to be 1, then that would give us 3, which is not congruent to 1 modulo 5. But if we use 2, three times 2, we'll check to see if that's congruent to 1 modulo 5. That would give us 6 on the left, which is absolutely congruent to 1 modulo 5, because 6 and 1 have the same remainder when you divide them each by 5. So what that means is that the inverse of 3 modulo 5 is congruent to 2 modulo 5. Can anybody think of a value x that would satisfy this congruence? Well, 8's not in this set. It has to come from this set of residues. Yep. X would have to be congruent to 3 modulo 5. That's because if you do 7 times 3, you get 21, which is congruent to 1 modulo 5, because if you did 21 minus 1, you get 20, which is 4 times 5. Okay, so the inverse of 7 modulo 5 is 3 modulo 5.